In this lab, we're using Newton's second law and the energy principle to predict the motion of a mass connected to a spring and compare it to experimental data. My objective is to create a computer model to model the motion and calculate the different energies of the system, which is the mass, the spring, and the earth, and the motion is predicted using two forces, the weight force and the spring force. The model motion is compared to the experimental motion, and I found that the model is not as accurate as it could be, although it shows a general path for the motion of the mass. A better model would account for both the drag force and motion in the z direction. The fundamental principles used are Newton's second law in the form shown, where F net is equal to the force of the spring plus the force of gravity. The second principle used is the energy principle, shown here. In this case, the chosen system has no interactions with the surroundings, so the total change in energy must be zero. The experimental setup consists of the origin set at the fixation point of the spring, the x-axis as the horizontal axis and the y-axis as the vertical. The calibration stick has been set to 0.7 meters, the length of the spring. The mass is known to be 0.402 kilograms. The motion starts in what would be the third quadrant. It is important to note that for the purposes of the model, the motion takes place in two dimensions. After analyzing the motion, the important data is the initial starting point and the initial velocity, which are documented here. Also, the data points have been saved into a CSV file so that it can be compared next to the model motion. L naught and K are the final variables we need to solve for in order to move on to the Python file, and I chose to compute these using the data for time versus x position. Using the equation for the length of a period and solving for the average length of one period, the spring constant comes out to be 5.8798 newtons per meter. Since the mass is in static equilibrium at the beginning, the magnitude of the force of gravity equals the magnitude of the spring force, and setting the equations for these equal means it's possible to solve for L naught, which ends up to be 0.02998 meters. With these variables in mind, it is possible to create a model for the motion. The first part of the code is updating the initial conditions, as shown here. Here, I have added in the code for the force of gravity, spring force, and updated the position update equation in Newton's second law. I have also updated the code to update the spring. The added arrows showing the forces point as we would expect, as the spring force is a restoring force and points up, while the weight force points down. The next part of the code is applying the energy principle. This part of the code applies the equations for the kinetic, the change in kinetic, the potential energy, and the change in potential energy for both the gravity and the spring forces. Here is the plot of the different system energies as the model runs, and it is seen that the energy principle is satisfied. The total energy equals zero, as expected since there are no interactions with the surroundings. The potential energies rise and fall as the corresponding forces do work. For example, when the force of gravity is acting on the object, as it is when the spring is first let go, the potential energy of gravity is decreasing because the force of gravity is doing work, thus decreasing potential energy of gravity at the beginning. Then, when the spring begins to do work pulling the mass back and begins to lose potential energy, gravity begins to gain potential energy, which keeps the total energy at zero, which is expected. This path continues for the potential energies, and the kinetic energy also makes sense when brought in alongside these potential energies. As the mass moves to the right at the very beginning, the kinetic energy is positive, and when the spring force begins to do work, pulling it back to the left, the kinetic energy is negative. After reading in the position data from the CSV file, the model runs side by side with the experimental motion. This graph compares the experimental and model motions using Python with the experimental position in red and the model position in blue. It can be seen that even though they start off the same, as time goes along, the model data starts to follow behind, leading to major differences at the end. This could be attributed to the model chosen to model the motion. In the experimental data, a drag force is also acting on the object, and this impacts the object's motion. However, this force is not included in the model. Another fault in the model is that the motion also occurs in the z direction in real life. The mass not only swings up and down and left and right, but also backwards and forwards, and this motion is not accounted for in the model. The final question to look at is the difference between an oscillation period calculated using the x positions and one calculated using the y positions. I obtained a period of oscillation for the x data earlier and got t equals 1.6429 seconds. Following the same steps for the period of oscillation in y, I got t equals 1.5195 seconds. Ideally, the time for the periods would be the same since the period length depends on the mass and the spring constant. However, since the spring constant is found using t is calculated using the position data of the mass in the experiment. The length of one oscillation is the amount of time it takes an object to return to the exact same location. This is seen perfectly in objects that exhibit simple harmonic motion, where the object has motion in one dimension caused by a constant force. However, the motion of the mass in the spring we are studying doesn't display simple harmonic motion, as previously discussed, with the presence of drag force and motion in the z direction, and doesn't return to the same position every time, leading to the x and y positions reaching their peaks at different points.